Hi everybody. Welcome back to Dave's Math channel. I'm starting chapter 2 of the Math Lovers book. This is my new feature on my 3-volume series called the Math Lovers book, which you can buy on Amazon.com if you're interested. There's 3 volumes, the 3 volumes shown in this picture. First volume is more recreational. That's the one I'm going over now. I just finished chapter 1. I'm making a series of videos on the first 2 volumes. And the second volume, which I'll do later once I'm done with the first one, is a little more advanced. It's more academic. It includes things like calculus and functions and statistics. And the third volume is a problems and solutions manual. And this one has problems for the first 2 books as well as solutions to all the even number problems. And I think I should mention as well that there's a biography section at the end of the second volume, and every week I'm going to feature a different biography going in chronological order. There's 80 biographies of famous mathematicians, so I just did one on Pythagoras, and anyway, you can enjoy that feature as well. But for today, I'm gonna do my first lesson on natural numbers, and that's on figure numbers. I have several parts to this. There's the first section's on figurative numbers, but there's like 3 or 4 different kinds of figure numbers I'm going to talk about today. I'm just talking about powers. So anyway, let's just begin. And this is pretty basic. So like I said, this is my first section in the chapter on natural numbers. Figurative numbers are just numbers that you can represent by geometric figure. And it doesn't have to be like a square or a cube. It could be more complicated. It could be, first of all, it could be higher dimensional. You know, the higher dimensional analogs of squares and cubes are just powers. You could have arbitrarily large powers. But there's also things like triangular numbers and hexes and even 3-dimensional things like pyramidal numbers and tetrahedral numbers. I'll get to all that later. But today I'm just talking about squares and cubes, basically. So I think most of you guys probably know about these already. This is kind of basic review, but you probably know what squares are. Maybe you don't know where the name came from. But a square is just a number that can be that represents the number of objects. In this case, I'm showing them as circles that can be arranged in a square. That's where its name comes from. So the example on this slide is just 4 squared. And to get a square, you could multiply in general, when you have a rectangle, you're multiplying the number of elements of the length times the number of elements of width. You don't have to count all the elements. You probably learned this in grade school a long time ago. For instance, if you had a 6 by 8 rectangle, you don't have to count all 48 objects in the rectangle. You can just notice that it's 6 in one direction and 8 in the other direction. So the number of objects is the 6 times 8. In the case of a square, it's even simpler because the length and the width are the same in the case of a square. That's why this particular rectangle is called a square. A square is a geometric figure who, with all 4 right angles, also such that the length and the width are the same. In this case, 4. So I think you guys all know 4 squared is 16. You can verify this by counting all these dots, and you'll see that there are 16. But like I said, it's easier. You just have to know one side, in this case 4, and then you just multiply it by itself. 4 times 4, that's known as 4 squared. And in general, n times n, where n is an arbitrary natural number, could even be 0 if you like, but it's easier to picture if it's a positive number. If n is any positive integer, which we also call a natural number, then if you make a square, an n by n square, the number of elements inside is n squared. So that's nothing special, I don't think. And I probably didn't tell you guys anything you didn't already know. But then you can generalize this to higher dimensions, for instance, cubes. And since we're working with, since I can only show you 2 dimensions and every page of the book is only 2-dimensional, you have to be a little clever when you draw 3-dimensional pictures. You have to kind of show some perspective. So this is supposed to be a cube, but it doesn't really look that much like a cube. looks pretty stretched out. But if I show the circles in this case in four different colors, four different hues. I show them in red, yellow, green, and blue, or black. I think red, green, and blue, and black. And each color is a different depth. So not only do we have length and width, we also have depth. And in this case, the length, width, and depth. If it's a cube, they're all equal. Cube is just a three-dimensional analog of a square. So in general, a cube that where n is a natural number, you have an n by n by n cube, length n, width n, depth n, or height n, if you like. So in that case, the total number of little cubes inside of it, or the number of objects here. We're showing circles, but you're supposed to imagine them arranged in three dimensions. Maybe it's easier to think of these things as spheres rather than circles, since spheres are three-dimensional. But we've arranged them into a cubic array, and it's a 4 by 4 by 4 cube. So 4 cubed we write as a 4 with a superscript 3 to the right. By the way, powers are always written with a superscript to the right. So we would write, 4 squared is 4 with a superscript 2 to little 2 to above and to the right. And similarly, 4 cubed we write as 4 with a little 3 up to the right. So that's 4 cubed, and you can verify for yourself that 4 times 4 times 4, or 4 cubed, is equal to 64. And if you're kind of a masochist, you could count all the circles in this cubic array and find for yourself that there are 64. But that's how you do squares and cubes. And like I said, you can generalize this to higher powers even. But the problem with that is it's almost impossible for us to imagine objects in higher dimensions. I mean, mathematically, you can describe as many dimensions as you want. And I actually have a video on higher dimensions. You guys might want to watch that one. But 4 dimensions is what we usually call a tesseract, a 4-dimensional hypercube. We call it a hypercube in general if its dimension is greater than 3. I think we call it a tesseract if its dimension is equal to 4. And there's different ways you can think about the fourth dimension. You can think of it as time, or you could try to imagine a fourth spatial dimension, which I can't do. I think there are a few people who can. But so there's I can't. I mean, you can't. There's even pictures. You can even make a picture of a tesseract. But so like I showed you, cube, you have to reduce it down to 2 dimensions. You can do the same thing with with a 4-dimensional object, a tesseract in particular. Actually, it's better. I don't know if you guys have seen 3-dimensional models of tesseracts. You can do it with soap bubbles. You can dip a cube in soap, and then what you see when you do that sometimes is you see a little cube inside the big cube, and then there's edges connecting the little cube and the big cube. And actually, that is actually a projection onto 3 dimensions of a 4-dimensional tesseract. And there's other ways you can project it as well. But anyway, enough about that. If you wanted to know how many objects there were in a tesseract that's 4 by 4 by 4 by 4, well, it's just 4 to the 4th power. So in general, 4th power would be n to the 4th, or n times n times n times n. And there's no reason to stop at just 4 dimensions either. You can go to as many dimensions as you want. For instance, 6 dimensions, if you had a 6-dimensional object whose size was 10, then the number of elements in that would be 10 to the 6th, which is equal to 1,000,000. And you could do as high powers as you want, and many objects as you want. So those are powers. And that concludes everything I have to say for today. Like I said, these will get a little more advanced in the next couple upcoming videos where I'm going to continue my series on figured numbers. But anyway, that concludes my video for today. So thank you for watching. Long live math. Once again, check out my series. And I'll see you guys next time. Bye.